We will now discuss igneous rocks. So this should be something that you've started talking about in lab. So 2 weeks ago, you all were identifying rocks or minerals and igneous rocks in your lab, and then this upcoming week, depending on how they reorganize labs because of the hurricane, you'll be looking at metamorphic and sedimentary rocks. So today we'll hopefully go into a little bit more detail than what you did in lab to discuss igneous rocks, and then possibly get into volcanoes. Alright, so igneous rocks are rocks that form through the cooling of magma or molten rocks. Once the magma gets to the surface, it is then called lava. So there is a differentiation between the two. So we have two major types of igneous rocks. We have extrusive and intrusive. Extrusives form at the surface, intrusives form inside the earth. I always like to think of this as intrusive is inside and extrusive is exiting and therefore is on the outside of the planet. So just little ways to help remember the difference. So let's first look at intrusives. So intrusive cools beneath the Earth's surface. And so it has a long time to cool. And it forms or cools in a couple of different locations. So ultimately, these are molten rock. So they are magma coming up from the mantle or remelting of rocks within the crust. And so then as they cool, as they get closer to the exterior of the earth, to the exterior of the crust, sometimes they don't make it all the way out. And so they cool in a couple of different locations. We have plutons and batholiths, which are the larger sections. It's a part of the magma chamber that has cooled. Then we have dikes and seals. So dikes and seals would be the pathways that magma is following to get to the surface. And so a seal runs a seal runs parallel to the rock layers, and a dike runs perpendicular. So let's look at these a little bit more. So igneous dikes are cutting across the pre-existing layers of rock, and sills are running parallel to the pre-existing rock, or we call it the country rock. So we are looking at these pathways as the magma is moving towards the exterior of the earth. It is finding the easiest pathway to follow. So sometimes there's pre-existing cracks or weak points along the rocks that will open up. So in the case of a seal, it is the cracks or the separations of the layers, the boundaries of the layers, can be broke open because they're two different types of rock, therefore relatively easy to break. And sometimes with dikes, they're cutting across the layers, so you get rocks that are relatively weak or easy to melt and create these pathways, or already have pre-existing cracks. So these are following the easiest pathways. Now plutons form really deep in the earth, about 8 to 10 kilometers. And so because this is moving up through the mantle and starts to go through the rock, the crust, the crust is brittle and therefore starts to fracture and break as you get this magma coming up towards the surface. And so because we have a brittle system, those crack, which allow the dikes and sills to form. And eventually, those dikes and sills can grow quite large and pass through the entire crust. All right, so here's another view. These are, just to remember that these are three-dimensional. And so as you have your plutons or your batholiths in the case of a huge magma chamber, and these are moving through the three-dimensional system of rocks, of the country rock. So if you look up over by the volcano, you can see the stalk in the main chamber going up. But as volcanoes cool and die, the sedimentary layers and the pyroclastic flows and the materials that the volcano spews falls out, and as it cools and dies, um, it's left with a series of these dikes, and they're radiating out from the cone or the center of the volcano. And you get these really interesting and pretty neat looking dikes that are radiating out of the center of a system. So it's one of the features that gets left behind and can be exposed at the surface because of erosion of that volcano. Now, sometimes these batholiths, plutons, sills, and dikes get exposed at the surface through erosional properties and uplift of the continental crust. So that would be our intrusives, the ones that are forming inside the Earth. Now let's look at extrusive. So these are cooling at the surface of the Earth, meaning they cool quite quickly because there's a large temperature difference between air and water and then the rock itself. Rock is a really good heat sink, and so it holds heat quite well. Whereas when magma, or in this case lava, starts to interact with air, it starts to cool quickly. And even more so if it starts interacting with water. So we get eruptions out of this. So we have two different types of movements of lava across the Earth. We have lava flows and explosive eruptions. So what do you think the difference is? All right, so when you add water and other volatile gases into the system, you can create an explosive eruption. So let's look at our different types of extrusive systems. So we have flows and eruptions. So first we'll look at flows. So this can be separated into basaltic, flood basalts, and pillow basalts. All flood basalts is as you have magma coming to the surface and lava starting to move over the surface rather slowly, it cools. And so if it is on land, it will start to form a flood basalt. And you, just like a failed rift system, that we start to try to make a spreading center, but it's the failed part of the three-parted ridge system. There is flood basalts there because you have magma coming to the surface and then flowing to the low point, so you get these large deposits of basalt on land. And we have two different examples here: Deccan Traps in India and the Columbia River system in Oregon, Washington has these represented. Then we also have flows that are underwater. And so with flood basalts, because they're exposed to air, they cool much slower than if it is exposed to water. And therefore we get these large flood basalts. But as we have magma and lava traveling across the surface underwater and erupting quite slowly, then you get pillow basalts. And this is where you have magma, really hot magma, interacting with water, so it's cooling it extremely quickly, but there's still magma behind that cooled material, and therefore it pushes it. And so you end up with a lot of these fractures in this system. All right, so let's watch one. I'm actually going to let you watch this on your time so we can continue talking. But please watch these videos. I'm going to skip over them in this discussion part. So here would be the video. Watch it on the presentation that will be on Moodle. All right, so now we have explosive. igneous rocks and extrusive rocks. So this is where we have volcanic eruptions that are quite explosive. So again, that is from there being water and other volatiles in the system. And we would create things like ash layers that can be seen or represented in between other rock types, tuffs or pumice, and depending on the different types of lava and magma and their composition, we can end up with scoria, breccias, all sorts of different types of explosive rocks. So what is happening is you have magma coming up out of the system, and you can have a different type of intrusive plutonic rocks, which would be the rocks that form in the pluton itself, so granite, diorite, or gabbros. And depending on its mineralogical content, it will have a color differentiation, where granites are very light with a couple or a few darker grains. But because they compose mostly of feldspars and plagioclase, which are a light in color mineral, and also quartz, which is light in color, it is mostly considered light. And then as we move through diorites to gabbros, we're getting more mafic or heavier in minerals, meaning that the magma originates deeper into the mantle or hasn't incorporated the continental crust at that point. So we have our different types. So we'll skip that. All right, so we have so we've moved on now to talking about how we can classify these by our chemical composition. So we have our grain size, intrusive versus extrusive, which is how quickly these minerals cool and how large the grain sizes are, which we'll get into our specific vocabulary for in a moment. So we have our different chemical compositions for our igneous rocks. So this can be broken up into felsic and mafic. We also have an intermediate, which would be a mix between the two. And then we also have ultramafic, which means no quartz and no silicon almost. So with felsic, it is very rich in silicon, oxygen, and aluminum, meaning it is light in color, which also comes to that it has low density. It is high in oxygen, high in silicon. And so it is mostly what makes up our continental crust. So our two examples would be granite if it's intrusive and rhyolite if it is extrusive. So they're still similar in chemical composition, it's just grain size is different. So we have mafic, which would make up mostly our oceanic crust. So low in silicon, no quartz. It's darker in color because it's more abundant in magnesiums and irons. And so we can use color to help us identify whether it is felsic or mafic, and also give us indications as to what the chemical composition is. So we can also look at cooling rates. So if it cools really slowly, it can be intrusive, and if it cools really quickly, it can be extrusive. Now these happen to both mafic and felsic type rocks, and so depending on the type of eruptions and magma they come from, then they will represent these crystals differently. So if the rock has a lot of time to cool, it will have larger crystals and coarser grains because those crystals can grow and have time. Whereas if it moves very quickly and the magma and lava move very, very quickly and cool very quickly, you'll end up with smaller crystals and very fine-grained systems. All right. So if we look at these, if you have you have a magma chamber, and say one part of that magma chamber gets isolated and cools really slowly, then we'll end up with our intrusive rocks. And so you have your main lava tube or magma tube that comes up, and then you eventually get to a point of eruption of the volcano. And so you can end up with extrusive pyroclasts, which are the volatile minerals that come out of the air. They get ejected really high out of the air, or into the air, and then fall back down. So volcanic ash, pumice rocks, any of them that hold a lot of air in them. And those can form different ash layers and rock layers. Then we also have our other extrusive rocks that will flow. So along with most volcanic eruptions, you have some form of pyroclastic gases and materials that are ejected, but then you have lava that flows out of the volcano itself. And those would be our extrusive rocks. And so if it's felsic, it'd be rhyolite. If it's mafic, it would be basalt. And then our intrusive rocks would be, our felsics would be granite, our mafic would be gabbros in that system. We also can get a intrusive porphyritic system, which is where we have large crystals in a smaller matrix. So a matrix, when we talk about minerals and rocks, is the fine-grained materials that you can't see as well or with the naked eye to identify what it is, but it has a larger grain system encapsulated or captured in it. So what this typically means is you have differential cooling. So you have some area where either there's pre-existing material that this extrusive or really quick cooling, so near the surface, but not exposed, cools rather quickly in the system. So typically it is a near surface quick cooling that has these larger grains in it. All right. So as we've hinted at and kind of started dancing around, we need lava. We need magma. And so ultimately we have to melt rocks. So we have a couple of different ways we can do that. We can increase temperature. So this is key to this system, is you have to have a heating source. Rock doesn't melt easily. So we can start melting rocks by either being deeper into the earth or near magma. And so one of the neat things is that different minerals have different melting rates. And so they melt at different temperatures. And so felsic rocks with higher silica in them melt at lower temperatures than mafic rocks. We can change the pressure in the system. So with materials at high pressure, they won't start melting unless if temperature is extremely great. So even if a rock is at its melting temperature, if there is enough pressure, then it can maintain a solid. That's our inner solid iron core in our Earth. It is solid because the pressure is so great that it overcomes the temperature and maintains the material as a solid. So if we decrease the pressure or the confining pressure, that material can start to melt. And we can do that. So we can melt rock too. We also can add water. So at subduction zones, where you have oceanic crust in the system, or being subducted back into the mantle, that oceanic crust has been at the bottom of the ocean and therefore saturated in water. And that decreases the melting temperature of the rock by, 100 degrees and sometimes even a couple of 100 degrees. So we have 3 different ways we can melt a rock, and often it's a combination of 2 or even all 3 of this system. So let's look at a couple of different areas this can occur. So in a spreading ridge, what we get is decompressional melting. So you have a magma chamber of mantle material that is already quite warm and hot and is behaving plastically. Again, it is able to move and flow, but it's still a solid. It's not mantle. Either there is a magma chamber that starts very deep towards the core mantle boundary and comes up, or because you have a system that has, or because of the mantle convection, you start ripping and pulling apart the crust, it gets thinner there. And because it gets thinner, you decrease the amount of pressure applied to the mantle and lithospheric and asthenospheric material beneath, and therefore you can get decompressional melting. And then this just self-perpetuates itself, where you have more decompression, you have heat from a magma chamber, and you just continue this cycle of heating, decompressional melting, and magma coming to the surface. And this is pushing and causing a spreading ridge to form. All right, we also have subduction zones, and so this would be fluid-induced melting. So like I was saying, you have oceanic crust being pulled and pushed underneath another plate, and so that is the downgoing plate is saturated in water. There's also oceanic sediments and continental sediments that have been redistributed across the ocean floor that is being subducted as well. And so that is typically felsic, or at least high in silicon, or if it is more oceanic based, it could be more calcium carbonates and dead organisms that have fallen out and been deposited. And so that has a relatively low melting temperature. So that's, as that is being subducted, the sediments that is being subducted as well start to melt first, because we have a very low melting temperature because of the water. And now we've started this system where we've increased the temperature because of that is melting. And then now some of the more basaltic material of the oceanic crust can start melting too. But overall, we start melting the sediment first, and then we can start eventually melting the slab, although that happens much deeper because it has to get warmer. So those are our main types of melting. Now, we've talked about different minerals crystallizing at different temperatures. This is known as Bohn's reaction series, where we have mineral crystallization and fractionation at different temperatures. And so this causes unequal separation of material. And so ultimately, we can start to look at the different rocks and minerals that we see and identify at what temperature it forms, which becomes really important for us when we want to tell the story of the rock. So, as magma temperatures decrease or get cooler, we have a very specific order of minerals that form. And we also can see that plagioclase will move from calcium-rich to sodium-rich as temperature cools. Again, affecting the composition and type of igneous rock that forms. All right, so a lot of times we can start to see this on our outcrops as we map them through the system. So in this example, we have a basaltic intrusion in this system. And in that, we have gone through and identified the different minerals in this system. And so it goes from a basalt, and then we start to see as we get higher in elevation, we get an olivine layer, and then we get to a calcium-rich feldspar, then a sodium-rich feldspar, and then basalt again. And what this is as the igneous intrusion cools, it then is, those minerals are falling out of solution. So we can see this here where, our mineral or our magma solution is at 1200 degrees Celsius and olivine starts to form. Well, those crystals then fall out of solution and collect at the bottom. And then as we continue to cool, we get pyroxenes and plagioclase feldspars doing the same thing. And then we cool even further to 600 degrees and we have plagioclase feldspars in the system. And so we can follow this throughout these rock materials. And so if we see this organized, layered minerals in these rocks, we can then say that this magma cooled rather slowly because we see this division, and olivine cools first, and then we get more calcium rich, and then we get plagioclase feldspars, and those all are starting to cool and get these nice layers. Whereas if we had a very quick cooling in these igneous intrusions, then all of these minerals would be mixed together. And so we can look at how fast did these cool. All right, so we can do that. Now, none of that thus far has formed something like granite. Granite is very light. It is felsic, high in silicon, which doesn't come from the interior of the earth. So how do we get it? So what we have is we have a basaltic magma chamber that is coming up, and we have another magma chamber. And so that is melting the country rock, so the rock around it. And so what it does is it starts incorporating the material and the minerals that are in that country rock. And that mixes into the solution because you have a system that is very light. Remember, those quartz and lighter minerals melt first. They have a very low melting temperature. So in the country rock, the very felsic, the very light, the quartz melts into that system first and reincorporates into the magma. And so we have a basaltic magma and then a magma that is this nice concentrated solution of silicon, oxygen, and very light minerals. Just all said that. And then eventually this breaks through and we get a nice mixture. And so we're adding more basaltic material that makes it into the andesitic mix and ultimately makes it into granite. All right, so we have a bunch of different types of rocks and we have our different locations that they can occur. So our felsic rocks, of course, will happen more on our continental crust. And our mafic rocks will happen more at our spreading ridges and also in our hot spots. But anywhere that we have subduction, we can also have an intermediate rock or even a mafic rock.